If you look at how the humanoid robotics industry is evolving right now, one thing becomes increasingly clear. We are at the very beginning of an enormous technological leap, and Tesla, under the leadership of Elon Musk, is gradually establishing an increasingly strong position in this race. Just a few years ago, Tesla Optimus was viewed by many as an experiment or even a marketing stunt. Today, however, the situation has changed dramatically. According to reports and publications from outlets such as Bloomberg, Reuters, and The Information, the company continues to invest heavily in the development of its humanoid robot, placing particular emphasis on its appearance, mechanical movement, and interaction with people. Whereas the primary focus once centered on functionality, the ability to lift objects, walk, and perform simple tasks, the emphasis is now gradually shifting towards something far more ambitious, giving the robot the most human-like appearance possible. The key element in this effort is the development of synthetic skin, capable not only of visually imitating human skin, but also of reproducing the sensation of touch. Why does this matter at all? Because appearance and tactile interaction represent the next level of trust between humans and machines. A robot that looks like a metallic machine is perceived as a tool. A robot that looks and feels like a human begins to become part of the social environment. This is why, according to industry insiders and analysts, Tesla is now actively studying developments in synthetic skin technologies that have been advancing for several years in China and Japan. In these countries, major research centers and companies have long been developing what is commonly known as electronic skin, or e-skin. This multi-layer material is capable of responding to pressure, temperature, humidity, and even microscopic vibrations. In Japan, such technologies are being developed primarily for medical robots and advanced prosthetics. In China, they are being created for humanoid platforms and next-generation service robots. And now, judging by current developments, Tesla appears to be incorporating many of these concepts into its own ecosystem. It is important to understand, however, that creating synthetic skin is far more complicated than simply producing a soft outer covering. It represents one of the most difficult engineering challenges in modern robotics. First, the skin must consist of multiple layers. The outermost layer is responsible for visual appearance, determining texture, color, and the way light reflects from the surface. It must look as natural as possible, featuring microscopic pores, subtle irregularities, and realistic responses to changing lighting conditions. Achieving this alone is extraordinarily difficult because human skin is one of the most complex natural materials known. Beneath that lies a layer of sensors, and this is where the real engineering challenge begins. These sensors must detect pressure at varying levels of sensitivity, distinguishing between a gentle touch, firm pressure, and sliding contact. Moreover, they must operate in real time and continuously transmit data to the robot's central control system. Below that is a layer responsible for elasticity and long-term durability. Unlike humans, a robot is expected to work around the clock, performing thousands of repetitive movements every day, meaning its skin must withstand constant mechanical stress without degrading. Finally comes integration with the robot's mechanical structure. The skin cannot simply rest on the surface. It must stretch, compress, and move together with the joints without forming wrinkles, tearing, or losing its functional properties. This is where one of the greatest engineering challenges emerges, combining softness and sensitivity with exceptional strength and resistance to wear. Now imagine how such technology could transform the design of Tesla Optimus. Above all, it would eliminate the perception of the robot as merely a machine. Exposed metal panels and rigid mechanical joints would gradually disappear, replaced by a smoother, more organic silhouette. The overall lines would become softer, and transitions between body sections would appear much more natural. The hands and fingers would likely undergo the most dramatic transformation. It is already well known that Tesla places enormous emphasis on Optimus's manipulators, and for good reason. The hands are the robot's primary means of interacting with the world. With the introduction of synthetic skin, the robot's hands would not only look human, but also function on an entirely new level. Imagine a robot picking up a fragile object, such as a glass, without crushing it because it can sense pressure, or, on the other hand, firmly holding a heavy object while adjusting its grip strength in real time. Furthermore, it would gain the ability to recognize textures, smooth surfaces, rough ones, soft materials. All of these would become part of the robot's sensory perception, and this opens up entirely new use cases. Robots could work in caregiving, assisting elderly people, and interacting with children. They could perform highly precise tasks that require delicacy. They could become part of everyday life rather than being limited to industrial environments. But along with these opportunities come significant challenges. The first is energy consumption. All of these sensors, data processing, and continuous signal transmission require power, while the robot must remain autonomous. The second is computational demand. Processing tactile information generates an enormous stream of data, and this is where Tesla would likely leverage its expertise in neural networks and AI to efficiently interpret those signals. The third challenge is reliability. The skin cannot fail after a week of use. It must continue functioning for months, or preferably years, under a wide range of conditions. The fourth is cost. These technologies remain extremely expensive, and Tesla's challenge will be to scale them and make them suitable for mass production. Here, the company has one major advantage: its experience in scaling complex technologies. What Tesla accomplished with batteries, electric vehicles, and manufacturing as a whole could very well be repeated here. This raises the biggest question: when might we see an updated Optimus design? Based on the company's current pace of development and public statements, the first elements of a more human-like design could appear within the next 1 to 2 years. However, the full integration of synthetic skin is most likely a much longer-term objective. The most realistic scenario is gradual implementation. First, individual components such as the hands, fingers, and possibly the face. Then, expansion across the entire body. Somewhere within the next 3 to 5 years, we could see a version of Optimus that comes remarkably close to a human being, not only in the way it moves, but also in the way it looks. And if that happens, it could become one of the most significant technological milestones of the decade, because at that point, the boundary between humans and machines would begin to blur not only functionally, but also visually, tactily, and socially. And Tesla, judging by its direction, appears to fully understand just how important that moment could be. The company is not simply building a robot, it is creating a new type of interface between humans and technology. And synthetic skin is not just another material, it is the key to transforming a robot from a machine into a natural part of our world. Essentially, we are no longer talking merely about the appearance of a robot, but about the creation of an entirely new class of devices that will be alongside people every day. And this is exactly where synthetic skin begins to play not only an aesthetic role, but also a strategic one. Imagine a realistic scenario in the near future: a home where Tesla Optimus is at work. It does not simply move objects or carry out commands. It interacts with people, it approaches them, hands them items, and assists with everyday tasks. At that moment, it becomes critically important for every interaction to feel natural. If the robot is cold, rigid, and metallic, it creates a barrier. Even if it performs every task perfectly, people will subconsciously keep their distance. But if the robot's surface is soft, warm, and responsive to touch, perception changes dramatically. That is why many analysts, including experts from MIT Technology Review, have noted that the next stage of humanoid development is no longer intelligence or even mechanics, but touch and social perception. Tesla, judging by its direction, appears to understand this very well. Now let's examine how such skin could actually work in practice. One of its key elements would be so-called sensor arrays. These consist of thousands, or perhaps even millions, of microscopic sensors distributed across the entire surface of the skin. Each one detects pressure, temperature changes, and vibrations. When a person touches the robot's hand, the signal is transmitted to the system instantly. But then, the most difficult part begins: interpretation. Because a touch is not merely a physical parameter, it carries context. A gentle touch means one thing, a firm grip means another, a sliding motion means something else entirely. The robot must understand the difference. This is where artificial intelligence comes into play. Tesla could use the same principles employed in its autopilot system, neural networks trained on enormous datasets. Only this time, instead of camera data, they would process information from the skin's sensors. In effect, Optimus would be learning how to feel. And that opens extraordinary possibilities. For example, the robot could automatically adjust its grip strength for a specific object, or recognize when someone accidentally touches it and respond appropriately by stopping, stepping back, or changing its behavior. Furthermore, it may eventually gain the ability to provide feedback. In other words, the skin would not only sense touch, but also respond. For example, by producing subtle vibrations or changing its temperature to create a more natural feeling of interaction. This goes far beyond conventional robotics and moves toward the field of neural interfaces. But along with these possibilities comes another important consideration: psychology. There is a well-known phenomenon called the uncanny valley. It describes the discomfort people experience when something looks almost human, but not quite. This is where Tesla will have to proceed very carefully. If the skin appears highly realistic while the movements remain insufficiently natural, the robot will seem unsettling. If the appearance remains too artificial, much of the intended effect will be lost. Finding the right balance may become one of the greatest design challenges. Now let's look at the competition. In China, companies are already making significant progress in developing humanoid robots with elements of synthetic skin. Some startups have demonstrated prototypes with faces covered in soft, skin-like materials. In Japan, these developments have gone even further, with robots capable of mimicking facial expressions. However, many of these projects face the same challenge. They often remain demonstration models and never reach mass production. This is exactly where Tesla could play a decisive role. The company possesses something that most competitors lack: the ability to scale complex technologies. If Tesla develops a practical solution, it could introduce it into manufacturing, reduce costs, and transform it into a mass-market product. That alone could reshape the entire industry. Imagine that within a few years, robots emerge that not only perform work, but also look, feel, and behave like humans. Such a development would fundamentally transform the economics of labor. The fields that were previously beyond the reach of automation, elder care, customer service, and education are becoming accessible to robots. But along with these opportunities come significant challenges. The first is ethical. How acceptable is it to create robots that look like humans? Where should the line between machine and human be drawn? The second is social. How will the job market change? Which professions will disappear, and which new ones will emerge? The third is safety. The more complex a system becomes, the more potential points of failure it has. Synthetic skin consists of millions of components, and each of them can potentially fail. And finally, there is the question of trust, because at some point, people may begin to perceive a robot not as a tool, but as someone, and that fundamentally changes the nature of human-machine interaction. Now let's return to Tesla. Judging by current trends, the company is moving toward the gradual evolution of Optimus. First came the basic functions, then improvements in mechanics. Now the focus is shifting to appearance and tactile interaction. And the next logical step is integrating all of these capabilities into a single unified system. A robot that can see, feel, move, and interact. And if Tesla succeeds in bringing such a product to mass market, it will not simply be another gadget. It will represent an entirely new category of devices. And perhaps synthetic skin will become the key element that finally transforms a robot from a machine into something much closer to a human presence. At that point, the question will no longer be, can a robot replace a human? But rather, how exactly will we live alongside them? However, the most interesting developments may begin not when Tesla learns how to manufacture synthetic skin, but when the company combines it with its other technologies into a single intelligent system. After all, artificial skin by itself is merely an outer shell. The real revolution begins the moment that shell becomes part of the robot's vast digital nervous system. One can imagine that each palm of Tesla Optimus will eventually contain tens of thousands of sensitive elements. In essence, the entire surface of the hand will become one enormous sensor. When the robot picks up an object, Information will simultaneously flow from thousands of contact points. Artificial intelligence will analyze this data almost instantly, determining the object's shape, weight, material, temperature, and even its likely fragility. For example, if Optimus picks up a porcelain cup, the system will immediately recognize that applying excessive force would damage it. On the other hand, if the robot is carrying a heavy metal component inside a Tesla factory, the algorithms will automatically increase its grip strength and redistribute the load across all of its fingers. This is why many experts believe that the next major revolution in robotics will come not from more powerful motors, but from advances in sensory technologies. Another important area is temperature sensitivity. Imagine Optimus being able to detect surface temperatures almost as accurately as a human. This would allow it to work safely in industrial environments where components may be extremely hot or cooled to exceptionally low temperatures. The robot could automatically adjust its grip strength, change the way it grasps an object, or refuse to pick it up altogether if there is a risk of damage. Equally interesting is the possibility that such skin could feature built-in self-diagnostics. If a tiny crack, small tear, or malfunction in one of the sensors appears, the system would immediately detect the issue and notify the owner exactly which area requires maintenance. Over the long term, Tesla could go even further by developing a modular synthetic skin design. Individual sections could then be replaced in just a few minutes without completely disassembling the robot. This would significantly reduce maintenance costs and allow Optimus to operate with virtually no extended downtime. Another extremely difficult engineering challenge is preserving the appearance of the skin after years of use. Human skin constantly renews itself naturally, but a robot has no such capability. Engineers therefore need to create a material that maintains its structure after millions of bends at the elbows, knees, wrists, and fingers. According to engineering estimates, a single Optimus hand could perform hundreds of millions of movements over several years of operation. All of this places an enormous amount of stress on the outer covering. As a result, the material must simultaneously be soft, flexible, durable, resistant to ultraviolet radiation, moisture, household chemicals, temperature fluctuations, and mechanical wear. Color presents another equally challenging problem. At first glance, it may seem sufficient to simply choose a shade resembling human skin. In reality, however, human skin appears completely different under sunlight. Artificial lighting, in the evening, in the morning, or in the shade. That is why materials specialists work not only on color, but also on the way the surface reflects light. This is precisely what makes human skin appear natural. If the light reflection is incorrect, the robot will immediately look artificial. Tesla is well known for paying extraordinary attention to the industrial design of its products. The company's vehicles are engineered to look modern even years after they are released. For this reason, many analysts consider it entirely plausible that the same philosophy will be applied to Optimus. It is even possible that in the future, the company will introduce several different exterior appearance options for the robot. For example, the industrial version would retain a simpler appearance with exposed technical components, since its primary purpose would be factory work. The home version, on the other hand, could feature an almost completely enclosed body, smooth contours, and a synthetic skin covering, making the robot appear significantly more friendly and approachable. This would also help reduce the psychological barrier between humans and machines. In addition, synthetic skin could greatly improve safety. Today, most industrial robots operate inside protective enclosures precisely because their metal mechanisms pose a potential danger in the event of a collision with a person. A soft outer covering would significantly reduce the impact of accidental contact. If Optimus were to accidentally bump into someone with its arm, the impact would be far less severe thanks to the cushioning properties of the covering. This is especially important if Tesla truly plans to deploy Optimus in homes, hospitals, hotels, stores, and other public spaces. Of course, it is still too early to talk about a complete transition to synthetic skin. The company has not officially demonstrated a finished version of Optimus with such a covering, meaning that any timelines and the final design remain a matter of speculation. However, the overall direction of global robotics suggests that these technologies are becoming increasingly important. Chinese and Japanese research centers continue to publish new scientific work in this field, while major humanoid robot manufacturers are placing growing emphasis on tactile interaction. It is therefore entirely reasonable to assume that Tesla will move in the same direction, gradually combining its achievements in artificial intelligence, computer vision, high-precision actuators, batteries, and advanced materials. If the company succeeds in integrating all of these technologies into a single production product, Optimus could become not only Tesla's most capable humanoid robot, but also one of the most technologically sophisticated machines ever produced for the mass market. That is precisely why the next few years may prove decisive for the entire Optimus project. Every new Tesla presentation will be closely analyzed not only by the company's supporters, but also by engineers around the world, because even small changes to the robot's appearance could reveal just how far the development of synthetic skin has progressed and how close humanity has come to creating truly human-like machines.